we start chapter 6. If you have any question, you can ask me. Before chapter 6, we studied chapter 4, chapter 5 about threads and process synchronization, and this chapter is about CPU scheduling. Okay, we already know about CPU scheduling. Why do we need it? Okay, the process of context switching, the process of loading a program, and the program changes different states. Okay, so first it comes, the new process state is there when it is initiated, then it is in the ready state. From ready state it goes into the running state. Okay, so whenever a process goes from ready state to running state, how do we do it? This is what we are going to learn. Okay, what are the things we need to consider when we select a process from the ready queue and we bring it into the CPU. So what we study in this chapter is about CPU scheduling, okay, which is very important for multiprogramming, and multiprogramming means the capability to run more than one program at the same time. And when we mean at the same time, it means although we assume there is, let's say, one CPU, it can execute only one instruction at a time, so that will be only one program at a time. But because of context switching, very quickly it seems as if many programs are run at the same time. So right now, for example, I am running PowerPoint, which you can see here, but there are hundreds of other processes which are run by the CPU. So there is browser, each browser tab has at least one process, then there are plugins in the tabs. So maybe in my browser I am running about 50 or 60 processes. Okay, and then there are different applications like Microsoft Word. I have 2 or 3 documents of Microsoft Word open, which is each one a different process, and then I have other slides of PowerPoints and so on. So hundreds of processes are being run in my computer, even though there are not 100 processors. Okay, processors are maybe 4. For example, my computer is quad core, so there are 4 processors, but still they are able to handle all these processes because of the ability of multi-programming, which means to be able to run these programs at the same time because of context switching. So these things require CPU scheduling, and we have different algorithms for CPU scheduling which we are going to discuss here. So how do we select a CPU scheduling algorithm? Which one is doing best, which one is not doing as good? We are going to see what are the criteria. So we start with the basic concept. We know about a process which loads into memory and then it is changing states. So this process, for example, this vertical line, it shows the life of a process, part of the life of a process. So it was doing something, then it comes into the CPU and it executes these 2 instructions, the load instruction in the CPU, the add instruction into the CPU, which are executed by some register, okay, and store can be some memory location. So here, let's say it says that load some variable store, the data in the store location, and add into this register, okay, and then it needs to read from file. So when it was executing these instructions, it was in the CPU, that was the CPU burst. Now it is reading from file, it needs to read from file, so the process goes to the IO burst, which means it goes to the waiting state, and after the reading is finished, again it comes to the CPU burst. When the CPU burst is finished, because it needs some IO, so it waits for IO in the waiting state, then CPU burst, and finally again to the IO burst, etc. So what do you see here is, in single application you can have multiple CPU bursts and IO bursts, because it's very rare that an application is just using CPU burst. Normally an application needs something from the hard disk or from the user input, or it displays something on the screen. So these are waiting for IO. Now what is here, what is the objective of this diagram that we see on the right side? Because whenever the process it is on the CPU is busy, but when it waits for I/O, so the CPU is free from this process. In that case, we will be allocating CPU to another process. This is actually what the context switching is. So we have seen in chapter 1 that the objective or the goal of the operating system is to maximize CPU utilization, okay, and to have a control on the CPU burst, so that if there is any process which is in the ready state, the operating system will bring that process to the CPU without wasting any time. So the CPU must be kept busy all the time. So our main concern here is to see the CPU burst distribution. It should be as much as possible for running multi-program applications, or for in a multi-program environment, in a multi-program operating system, we will be using as much applications which are run by the user to be running on the CPU. Now, we already studied, yes, any question? So, okay. Okay, these are instructions which are run by the CPU. So, every program, when you write the program, let's say in C and C++, so you have printf and you have cout, etc. Okay, cin, and all those instructions we have add or multiply, etc. So when you compile that program and you generate assembly code, so these are assembly instructions: load, add, store, index, etc. Okay, those in black font, the dark font, they are actually the assembly language instructions which are executed by the CPU register. Okay. So it's not important for this course. This has to be done in, I hope you are studying the other course of computer architecture and assembly language. So you must know from there that these are assembly language instructions to be executed by the CPU. Okay? We studied about non-preemptive and preemptive kernels, okay, somewhere before. What are non-preemptive? In fact, it was in process synchronization, I think, in the last chapter. Preemptive kernels, we say that these are those kernels which can be removed or taken away from the CPU when they are executed, and non-preemptive ones are those which cannot be removed, which means that they will keep continuing until they finish their task. So here we differentiate between two types of scheduling. A preemptive, non-preemptive scheduling is one in which when you give the CPU to a process, okay, so the process will keep using the CPU until it leaves the CPU by one of two reasons. Either it leaves because it terminates, it finishes its job, or it leaves the CPU because it needs to go to the waiting state. It needs some I/O, so it goes to the waiting state. If a process can leave only because of these two reasons, then such scheduling is called non-preemptive scheduling. But if there is the case of interrupts, okay, or signals or traps by the operating system, then because of an interrupt, the process can leave the CPU early. Okay, in that case, this is called preemptive scheduling. We already know also about the short-term scheduler, okay, whose job is to select one process from the ready queue and allocate the CPU to this process. Okay, the important criteria here is how do we order the queue. What we know normally is only one type of ordering, which is first come, first serve. For example, in banks, okay, when you are waiting for your turn, or in any store, when you are waiting at the cashier, so you make a first come, first serve. The person who is at the head of the queue, he will get served and serve first, then the next person, and so on. And any new person who is coming to the queue, who is joining the queue, they will wait at the end of the queue until they become at the head of the queue. This is only one type of queuing that we know so far, but there can be other types of queuing that we are going to study in this chapter. So we need to make a decision about CPU scheduling, which means that when we need to allocate the CPU to a process. And here we see the 4 conditions. One type of scheduling, I mean when you give the CPU to a process, is when a process switches from running to waiting state. So when the process needs some I/O, it switches from running to waiting state. In that case, the CPU is free, so the short-term scheduler will bring another process to the CPU. The second possibility is when a process switches from running to ready state. Why? Because maybe there is no process in the ready state, or maybe there is some process, but because it has some property because of which this process will come to the head of the queue. So if it comes to ready state, it may be at the head of the queue, and maybe we need to allocate CPU to this process. The third option is when the process switches from waiting to ready state. So from running to ready state or from waiting to ready state. So in the second case, actually, you choose from running to ready, so the CPU is free, another process from ready can come to the running state, it can get the CPU. In the third case, because it changes from waiting to ready state, so maybe it is its turn. And finally, when a process terminates, it leaves the CPU and any other process can come. So these are the 4 criteria, and here we see that criteria 1 and 4, they are non-preemptive. What does it mean? Is that if, because the process leaves the CPU by itself, it is not taken by someone else, by the scheduler, for example, or the dispatcher or the operating system interrupt, etc. So the 2 and 3, criteria 2 and 3, they are preemptive, which means that in these cases the operating system has generated some interrupt and these processes have been switched from running to ready state or from waiting to ready state. Okay, so what do we need to consider when we have preempting scheduling? We must ensure the problems that may come because of the shared data, because the data may be shared between many processes. So if a process leaves the CPU, another process comes, we must ensure that the data remains consistent and it is not changed in a way that will create problem. We also need to consider the preemption while in kernel mode. So if a process is executing in kernel mode, it has access to special instructions. So when you remove the process from the kernel mode, what will happen? Will the task be completed or not? That is another issue. The third one is to consider interrupts occurring during crucial operating system activities. Any question? Okay. So if the operating system is doing some important activities and the operating system or the kernel is in the CPU, running in the CPU registers, and there is some interrupt, what will happen? These are just some aspects which we need to consider when the scheduling is preemptive. So this was about the CPU scheduling, and here we learn that what are the things which will lead to the scheduling of one process to the CPU or removal of a process from the CPU. There is an entity, okay, another component in the system which is called dispatcher. Okay, so dispatcher is actually that module which gives the control of the CPU to that process which was selected by the short-term scheduler. So what we understand from here is that the job of the short-term scheduler is to select a process from the ready queue. How does it select? It will use some algorithm which we are going to study next, but the job of this short-term scheduler is only to select a process. How this process goes from the ready queue to the running state in the CPU, this is the job of the dispatcher. So what does a dispatcher do? These are the 3 activities. The first activity, it is clear that it does context switching. Can anyone explain to me what is context switching?
Like you said before, when it's the process in the wait.
No, nothing in the wait. Yes, context switching. What is the concept? Yes.
When a process is too large, then the context switch puts some of it in the disk, right?
No, that is swapping. Okay, let me explain. If you remember, we taught this in chapter 2 and also in chapter 3. Context switching means that when you move a process from ready state to running state, okay, so we need to load the data from PCB into the CPU, okay, and before that, actually, if a process is running in the CPU, when you remove the process from the CPU, you save its context. You save the information about the program counter, the information about its various registers, the memory limits, etc. All those information you save it into the process control block. So the process which we are removing, we save the information into its process control block, and the next process which is coming, we load its information from its process control block. That is called context switching. Okay. So this dispatcher is responsible for context switching, which means loading and unloading the processes from the CPU and then switching to the user mode. Okay, so dispatcher itself is running in the kernel mode because it is part of the operating system. Okay, so when it loads the next process, it will change the mode to the user mode, and finally it will actually jump to the proper location in the user program, which means it will load the program counter, which will be containing the next instruction to be executed. So it will load the next instruction into the CPU, and the CPU will start from there. Now the important question here, after doing these three activities, it will take some time, and that time actually is known as this dispatch latency. So the dispatch latency is the total time which is there when you stop one process and when the other process starts running. This time, and this time is actually something which is not very useful. So I ask you a question. Dispatch latency is time. It can be big time, it can be small time, okay, more time or less time. So in your opinion, my question is what we want? We want more time to be better in dispatch latency, or the dispatch latency should be small?
Can you repeat the question?
My question is, you understand dispatch latency. It says that it is the time to stop one process and then start another process. In between these two, there is a time. This is called dispatch latency. So which one is better? If the dispatch latency is more, or if the dispatch latency is less? Less, yes, good. Why? Because this is not useful time, so we would like the dispatch latency to be less and less. If it takes more time in dispatching this thing, it means that we are wasting our time. Okay? So that is about dispatcher and dispatch latency. Now, before in the last slide, we studied that the CPU scheduling may be because of the algorithm that is used by the CPU scheduler. So what are the things we need to consider when we do scheduling? Okay, so normally we have these 5 criteria, and I'm going to explain what does it mean. The first criteria is CPU utilization, which means that any algorithm that we select for scheduling, it must try to use as much CPU as possible, to keep the CPU as much busy as possible. Okay, that's the first criteria. The second criteria is that of throughput, which means that the number of processes that will complete their execution per unit time. So let's say in 1 second, okay, how many processes can complete their execution? So if we have 2 algorithms, we compare their throughput. I ask you a question now about throughput. My question is, we have 2 algorithms, okay, scheduling algorithms, which are the short-term scheduling. One algorithm is using such criteria for throughput that it finishes 5 processes in 1 second, and the other algorithm, its throughput is completion of 7 processes in 1 second. Which one is better, the one with 5 or the one with 7?
With 7, right?
7, yes, because the more processes finish their execution, the better it is. We want to be as much working as possible. So finishing a process means we are working more, so higher throughput is what we want. So better maximize CPU utilization and maximize throughput. The third thing is turnaround time. The amount of time to execute a particular process. Okay, so how much time it takes to execute a particular process. So we would like this to be minimum. So which means that a process should be executed in as small time as possible. When it comes until it goes, this is actually the turnaround time. Waiting time is the amount of time a process was waiting before it goes into running state. So if a process is waiting long time, it means the algorithm is not good enough to serve the process. We would like to reduce the waiting time. But here we are talking about one process. In general, because there may be many processes, so we would like to consider average waiting time. So average waiting time should be as little as possible. Okay? And the final point is about response time. It is the amount of time taken by a process, okay, when a request was submitted and then the first response is produced. So let's say you double click a process, okay, to start a process. That is actually your request. You want to run the process. And then after a few seconds you see that there is, let's say you start Word. So before the Word is loaded, you see this, splash screen, the screen of the Word in blue color. Okay, that is the response time when you double click to run a process, and the time when you see some response. So we would like to minimize the response time. In small time, if a process is running and it gives you response quickly, it means the algorithm is better. But normally, let's say if you think that you double click on something and you are waiting for it to be loaded because of the scheduling, then it has a high response time, which is not a good thing. Now I gave you the example of double clicking and loading a process, but not always is this because of the CPU scheduling. It can be because of memory, it can be because of many other factors. Okay, but here on CPU we consider these 5. So the first 2, which is about CPU utilization and throughput, we are going to maximize them. Maximum CPU utilization, maximum throughput, and the turnaround, waiting and response times, we want to minimize them. Okay, minimum turnaround time, minimum waiting time, and minimum response time. So we will consider these criteria, okay, any of these criteria, to design our algorithm. We cannot consider all of them at once because they may have conflicting requirements. Okay, so we have to choose one criteria to actually design an algorithm and see which algorithm is better if we have this CPU schedule. Okay, so normally we choose waiting time because this one is the easier to measure. The other ones, they are not that easy, but we will see. So first, what are some of the algorithms? Here you see there is a list of 6 algorithms. The first one is the first come first served, shortest job first is the next one, then your shortest remaining time first, priority algorithm, round robin algorithm, and multi-level feedback queues. And we are going to study, inshallah, all of them one by one. So the very first algorithm is first come first served. Can you tell me what is first come first served? Any idea? You have already studied this before. First come first served. This is also known as first in first out. Yes? So write this is queue. Okay, so a queue is first come first served. You have a queue, and the process which comes first, it will be served first, it will be executed first. So here is an example. And what we consider here is on the top we have a table sort of. Okay, we have two columns. One is the process ID or the process number. So we have three processes, P1, P2 and P3. And the other one is the burst time. What is burst time? It is the time taken by this process on the CPU. Okay, in one go. So maybe like this burst time 24 for the first process, it can be millisecond or it can be nanosecond, microsecond, but it is any time unit. So this 24, it will be needed by the process in one go to complete its burst time. Okay, and maybe after that it may terminate or it may go to waiting state. Okay, or it may do something else, let's say. Okay, so here are three processes, and for each process we have burst time. Now the arrival order is such that P1 comes the first, then you have P2, and then you have P3. Okay, so what we learn here is that P1, because it comes first come first served, so it will go to the CPU. Now what we see here is called the Gantt chart. What is Gantt chart? It shows the activities timeline, which activity is taking how much time. Now here we assume that we start at time 0. Okay, so this is our start when the first process comes. Okay, so the first process is P1, we give the CPU to P1, so the P1 is executing here. This shows the execution of P1 on CPU, and for 24 microsecond or whatever time unit we have, let's say it is microsecond, so it executes for 24 microsecond. Then this process burst time finishes, which means that the CPU is free, and immediately we bring the next process, which is P2. P2 was in the queue next, so we bring P2. P2 executed for only 3 microsecond, it finishes, and then P3 comes, which is the last process, and it also spends 3 microsecond in the CPU. So overall it was 30 microsecond. Okay, now what we need here, okay, for this algorithm is to compute the average waiting time. So first we need to find the waiting time for each of P1, P2 and P3. So the waiting time for P1 is 0. Can anyone tell me why is waiting time of P1 0? Is the first one, it came, it did not wait, and it starts execution. Okay, good. So it did not wait at all. It directly came to the running state, to the CPU, and it executed for 24 microsecond. Now why is the P2 waiting time 24 microsecond? Why? Yeah, because it just came along with P1, but P1 started execution, and this one waited for 24 microsecond or 24 time units, so the waiting time is 24. Similarly P3, it waited for 27. All the P1, P2 and P3, they were here. We assume they come at the same time, but P1 started before, then P2 and then P3, so P3 had to wait for 27 time units. So this is 3 processes, and these are 3 time units. We find the average by sum, taking sum of the 3 and dividing by 3. So this gives us 17 time units. Okay, so this is the average waiting time when we consider the first come first serve. Now the order here is P1, P2 and P3. What will happen if we change the order? So let's assume that P2 goes first to the processor, then P3 and then P1. Now the chart is something like this. Okay, P2 is first for 3 time units, then P3 and finally P1. And this time the waiting time for P1 is 6. You can see because P1 started here, before 6 it was waiting. For P2 it is 0 because P2 started immediately. And for P3 it is 3 because it started after 3 time units. So again we take the average waiting time and this time the average waiting time is 3 only. Before, in the last slide, it was 17, the average waiting time. This time it is 3. So the average waiting time has reduced quite significantly. What does that mean? It means that when we change the order of the processes, the average waiting time is changed, of course, okay? But what do we learn from here? We learn that if the small processes, they come first, then the average waiting time will be less, okay? Any question?
No.
No, okay. So this thing, when the long processes, okay, they come first, and the short processes, they are waiting for their turn after the long processes. This is called Conway effect, okay? So Conway effect means that the long processes, they come first, and because of the long processes, the short processes have to wait for a longer time. So Conway effect is not good. We should eliminate the Conway effect, which means that we should consider the small processes. According to this criteria, we should consider the small processes first. So the first come first serve scheduling has this problem, okay? So they can consider that there is one CPU bound and many IO bound processes. Now CPU bound, if you remember from last chapter, in chapter 3 I think, okay, we know that CPU bound process is a process which has small CPU burst, but each burst is very long, okay? So small number of long bursts, this is the CPU bound. An IO bound process, it has many CPU bursts, but each burst is very small. So this is what we need to consider when we design the algorithm, that if a CPU bound process is before the many IO bound process, so those IO bound processes will be waiting. So the next process, this was about first come first serve. I think we should stop here, the first come first serve scheduling, and we will discuss the remaining scheduling next time, inshallah.
We stop here?
We stop here today, yeah.